Okay, let's continue with section 10 of the ZAERO advanced training. Here we'll review the fictitious mass method for dynamic loads analysis. So the concept of the fictitious mass method, let's review that. Now, because the modal approach often requires only a few lower order modes, the resulting deformation may not be able to capture the local distortion in the structure. However, local distortion may be caused by concentrated loads, and usually the lower order modes do not contain this type of local distortion in their mode shapes. So, the fictitious mass method creates a set of fictitious mass modes by first adding a large mass at the degree of freedom in the structural model where a local distortion is expected to occur, and then we compute the eigenvalues and eigenvectors of the structural model with the large mass. These eigenvectors are called the fictitious mass modes that contain the local distortion in their mode shapes. And then finally, we remove the large mass from the mass matrix to generate the generalized mass matrix, but we retain the fictitious mass modes. Now the equation of motion is constructed using the resulting generalized mass and stiffness matrices and the fictitious mass modes. The generalized mass matrix is no longer diagonal, but it does not introduce any numerical difficulties in solving for the response. And because of the local distortion in the fictitious mass modes, the resulting deformation can capture the desired local distortion in the structure, which leads to accurate loads prediction. So first we'll look at a simple example of why we need to use the fictitious mass method. This is a cantilever beam subjected to concentrated moment force at the tip. So for a cantilever beam, the boundary condition at the tip is given here, where the second derivative of h with respect to x is 0. So all natural modes of the beam satisfy this boundary condition. And if the modal approach is used to solve the response, then the resulting deformation also satisfies that condition at the tip. However, if we now subject this beam to a concentrated moment at the tip, the modal approach cannot give the correct solution because the correct deformation at the tip is not, the second derivative of h is not 0 because we're applying a concentrated force. Now the fictitious mass method can resolve this problem. What we do is add a large moment of inertia at the tip to create a set of fictitious mass modes by now solving the equation with this fictitious mass. Then we can generate the generalized mass without delta Iyy and the stiffness matrix using phi fictitious. So we take our original mass and stiffness, pre-impulse multiplied by the fictitious mass modes, and that gives us our new MHH and KHH. Now we can construct the equation of motion to solve the response. And that will allow us to recover the correct deformation while satisfying this condition. So let's look at an example of landing gear loads without aerodynamic forces. This is from the Nastran, MSc Nastran test cases. So we have 4 simultaneous forces applied in the positive z direction at these 4 locations. And the type of force is given here, so we have a 1 minus cosine force that's applied. F max is 100 newtons, omega is 9.35 hertz, and T naught is 0.5 seconds. And the results are shown for the vertical shear forces along the wingspan at the monitoring stations B, C, M, and O. Now, stations B and C are just before and after the first inboard point where the force is applied. M is outboard of the last point, and then O is much farther outboard. So the point O should not see the local deformations because it's far away from the concentrated forces. We're going to do the analysis with and without the fictitious masses, and we have 4 1,000 kilogram fictitious masses at the loading points in the z direction only for the fictitious mode shape analysis. The ZAERO results are compared to the solution 112 of MSc Nastran. the fictitious mass is removed in MSE Nastran by using the M2PP card, and the fictitious mass results are exact, which agree with Nastran's SOF results. So let's look at some plots here. For station B, with no fictitious masses, our peak force is about 125 newtons, and then at station C, with no fictitious mass, the peak force is also 125 newtons. But with the fictitious masses, when we compare stations B and C, station B, the peak force is 350 newtons, and station C, the peak force is 250 newtons. So this peak shear force computed by the fictitious mass are discontinuous. The jump in forces of 100 newtons is nearly the same as the applied force, and it's correct. Whereas with the no fictitious masses, stations B and C, the peak shear forces are nearly the same, which is obviously incorrect. Now we'll look at stations M and O. At station M, outboard of the excitation, the non-fictitious mass peak force is larger than the fictitious mass results because of the redistribution of the excitational forces. So with the no fictitious masses, our peak is about 50 newtons here, and with fictitious masses, the peak is about 40 newtons. And at station O, which is far from the excitation, the non-fictitious mass and the fictitious mass give similar results. So you can see these two plots visually, they look identical. So like I said, with station O, which is far outboard from the applied external forces, it doesn't matter if we use the fictitious mass mode shapes or not. We get the same results. Now if we look at the maximal shear forces along the wing with no aerodynamics, with the no fictitious masses, you can see that for the first and the second peaks are nearly continuous along the wing, which is not correct. However, with the fictitious masses, the first peak, you can see the jumps of 100 newtons here. And then our ZAERO and Nastran results agree very well. And then this is the second peak here. So obviously the with fictitious masses gives us the correct response.